So, to recap everything we did up till now, we found our derivative, we set our derivative equal to 0, and we got x equals 8. We also had to put 0 on our number line because 0 is a non-permissible value for our derivative. And we found out that it's decreasing before 0, increasing after, and then decreasing after that. Now, this kind of might make you think, if I look at this, it kind of makes me think of something like this, which if I have something like that, can you see that some parts are concave up and some parts are concave down? That would be sort of what an x cubed graph would look like. But when we did our second derivative, we got that it was never equal to 0. We did have a non-permissible value at 0, but in both sections, this thing is concave down. So now when we go to get our graph, we're going to find out all of these points. We already, I think we wrote it up above, we knew that when you plugged in 0, you got 0, 0. We also need to plug in 8. We know that at 8 we have a local maximum. I'll do that in blue. 8, and if you plug in 8 back into your original equation, what are you going to get? You know how to do mental math with fractional exponents? The bottom part is a cube root, the top part is squaring. So if I plug in 8 into the x to the 2/3, I would cube root first. Cube root of 8 is 2, and then I'd square, and that would be 4. 3 times 4 is 12, minus 8 is 4, so we have the point 8, 4 as a local max. So how do we go about graphing this completely? Oh, the other thing that I want to solve for all of this are our x-intercepts. If we set our original equation equal to 0, and we try to solve where is this all equal to 0, well, if I factor out an x to the 2/3, that's going to leave me with 3 minus x to the 1/3. We already knew it was equal to 0 at x equals 0. Where does this other part equal 0? When 3 equals the cube root of x, or when x is equal to 27. So those are our two x-intercepts. Putting this all together into a graph. What do we know so far? We know that we have an x-intercept at 0, 0. We have another one over here at 27, 0. We know that at 8, 4, we have a local maximum. We know that it always has to be concave down, and that it's decreasing, then increasing, then decreasing. What this graph looks like, if I draw to the right of 0, concave down through those points, that's what I would get. If I draw to the left of 0, concave down, but going up, this is what I would get. And we have a very interesting point happening at 0, 0. I don't know if this quite qualifies for the definition of a cusp, but I think it's close enough that we'll call it that for today. So when you get a point like the one that just happened there, I believe it's called a cusp. What a cusp is if both of these had a tangent that was kind of like that. Both curves separate at that point had that tangent, then that would be a cusp. You don't have to know what a cusp is. And I might have defined it wrong completely, so that's okay as well. Yes? There wouldn't be a vertical asymptote there because it's only a non-permissible value for the derivative. If we go back to our original equation, you can plug 0 in. It's fine. It just became a problem in our derivative. And because of that problem in our derivative, there is no derivative, there is no tangent at that point. And the reason there's not one tangent is the definition of a tangent is a line that touches the curve only once. Can you see that you could draw one here, or there? Like there's so many different ones that would follow that definition that there's not exactly one that works. So we say that the derivative doesn't exist at that point. That looks pretty. So it's kind of a different looking graph. Kind of fun. And our last graph, we're going to show in this graph that even though we can get the second derivative to equal 0, that this graph doesn't have an inflection point. So first of all, if I was looking at my first derivative, I would get 4x cubed. If I was looking at my second derivative, I would get 12x squared. If I put it equal to 0, it appears that there might be an inflection point at x equals 0. To show that something is an inflection point, we mentioned before, it's not enough just to show the second derivative is equal to 0. That's one thing you have to show. You have to show a second thing. The second thing that you have to show is that it changes concavity at that point. However, if I put 0 on a number line and I plug values in prior to 0 into my second derivative, well, anything less than 0 is going to be positive. That means this section is concave up. If I plug in a value after 0 into my second derivative, again, it's going to be positive. In fact, it's pretty obvious that 12x squared is always going to be positive, no matter what value you plug in. And so at 0, it doesn't change concavity, and so it won't be an inflection point. The other way that you can show an inflection point is first showing that your second derivative is equal to 0, but then you would also have to show that your first derivative doesn't change sign at that point. However, if we set our first derivative equal to 0, we get 0 there. Before x equals 0, plugging in a number into your first derivative will be negative, meaning this function is decreasing, and then after 0 is positive, meaning that it's increasing. So our first derivative does change sign at 0, which makes the point 0, 0 a local minimum and not an inflection point. As far as what this graph looks like, it's like a fat parabola. And so even though the second derivative is equal to 0, it's not an inflection point.